We are in Chapter 8, Hypothesis Testing. Section 8.1 is Basics of the Hypothesis. A hypothesis is a claim or a statement about a property of a population. Again, this is about a population. And it's a claim that we want to investigate. So it's what and we've seen this before in like science classes. Usually you have a hypothesis and that's what you're trying to test and see. So a hypothesis test, or a test of significance, is a procedure for testing a claim about a property of a population. So steps in hypothesis testing is we're going to make a statement regarding the nature of the population. We're going to collect evidence, which is going to be our sample data to test the statement, and then we will analyze the data to answer the plausibility of the statement. So next we have is a couple definitions. So we have a null and alternative hypothesis. And our null hypothesis is going to be denoted H0. And this is a statement to be tested. It is a statement that is assumed to be true until evidence indicates otherwise. And this is going to be our default. So this is our default hypothesis. And this is what we are currently accepting. Okay, versus our alternative hypothesis, which is denoted H1. We also see this sometimes in other books or other resources as H sub A. And so this one, though, that our book is using is H1. And is the hypothesis that the sample observations are influenced by some non-random cause. And this is what you're trying to test. So the null and the alternative hypotheses are huge for hypothesis testing. This is going to be how our problems start out. We are going to state what a null hypothesis is and what the alternative hypothesis is for the problem. So right below this it says, for example, suppose we want to determine whether a coin was fair and balanced. A null hypothesis might be that half the flips would result in a heads and half of them would result in tails. The alternative hypothesis might be that the number of heads and tails would be very different. Or maybe there's more heads than tails when we flip, or vice versa, more tails than heads. Symbolically, these hypotheses can be expressed as, and you'll notice I have my H0 and my H1 here. And you'll notice that I have a P. That P is standing for proportions. That is one of the variables that we might be using. Another variable that we could be using besides P would be mu for our mean, sigma for our standard deviation, or sigma squared for our variance. Again, I'm using the variables for a population because we're testing about a population. So H0, if you notice also, we always have an equal sign. So that will always hold true. Our alternative, though, is going to matter about the wording of the problem. So no, you're not going to be using all three of these symbols in here. You are going to select one. And that one would be based upon the wording in the problem. So maybe it might say there are more heads than tails, or more than half of the proportions of heads would be greater than 50% or 0.5. And we would use that greater than symbol. So again, carefully reading the problems to figure out which symbol to use. So we have three ways to set up a null and alternative hypothesis. So our first one is going to be if the equal hypothesis versus a not equal hypothesis. This is called a two-tailed test. And because we are still dealing with data that is going to be normally distributed, two-tailed test means that we're going to have a little bit in each of these ends, and this is going to be where H0, our parameters can be equal to some value, and our alternative is going to be that it's not equal to. So something smaller, something larger, and that's why it's two-tailed. The second one that we have is equal versus less than, or a left-tailed test. And for this one, since it's a left-tailed test, you'll notice that our symbol here for our alternative is going to be less than. So we will be dealing with that left-tailed. And then the third one we have is equal versus greater than, or a right-tailed test. So H naught, again, is still going to be equals to. But this time with our bell-shaped curve, since we're dealing with greater than, we're dealing with that right tail. One thing to note on here is that our null hypothesis is always going to have an equals to sign. And that's going to be for our null hypothesis. Your alternative hypothesis, or H1, depends again on that wording. If you have a two-tailed, left-tailed, or right-tailed test, is going to depend on the symbol that we have. So again, not equals to will be two-tailed. Less than is our left-tailed test. Greater than is our right-tailed test. So right below this we have an example that says the null and alternative hypotheses are given. Determine whether the hypothesis test is left-tailed, right-tailed, or two-tailed, and then what parameter is being tested. Again, these parameters that we have are going to either be P for proportions, mu for mean, sigma for standard deviation, or sigma squared for variance. So for part A, we have H naught is P is equal to 0.2, and our alternative H1 is P is less than 0.2. And since we have a less than symbol, that means that we know that this is a left-tailed test. And then the parameter that we're using, it is a P, and that P stands for proportions. So that's our variable or our parameter. For part B, H naught is going to be sigma equals 0.76, and H1 is going to be sigma is greater than 0.76. And we have a greater than symbol in here, and so that means that we have a right-tailed test. And then the parameter that we are dealing with this time is sigma, and sigma stands for the population standard deviation. So this is standard deviation. On the next page, we have another example that says determine the null and the alternative hypotheses. So part A says according to the National Association of Home Builders, the mean price of an existing single-family home in 2009 was $218,600. A real estate broker believes that because of the recent credit crunch, the mean price has decreased since then. So I'm going to go ahead and write down H naught and H1. And the first question that I always ask is, what parameter is it that we are discussing? And since it is saying the word mean in here, if you read it, it will say that the mean price, and so we'll be using mu, since we're talking about the mean. Our null hypothesis always has an equal sign, and our alternative depends on the wording in the problem. And for this, if you read the last sentence, it says that the mean price has decreased since then. So we're going to say less than. And that value that goes in there is the amount that we thought that it was, which is going to be that in 2009 was $218,600. And the number that you put here needs to match the number that you put down here. So this is our null and alternative hypotheses for this problem. Part B says in 2010, the standard deviation SAT score on critical reading tests for all students taking the exam was 112. A teacher believes that due to changes in high school curricula, the standard deviation of critical reading test scores is different than it was in 2010. So again, null and alternative, write down H naught and H1. First question is going to be, what is the parameter that we are discussing? And if you notice, it does say standard deviation. So I'm going to go ahead and put sigma, which is our population standard deviation. That is our parameter. Again, H naught always gets an equal sign. And then I have to read the problem to figure out what symbol to put for our alternative hypothesis, or H1. And the last part of this says that the standard deviation of critical reading test scores is different. And different is a word that we would use for not equals to. It doesn't say greater than or less than, it says different. So we don't know if it's smaller than or more than, but something is not the same as 112. So that number that we have is 112. So I'm going to go ahead and put that down for both of these. And this is our null and alternative hypotheses for this problem. So we have 4 outcomes for hypothesis testing. So we can reject the null hypothesis when the alternative hypothesis is true. And this is great. This decision is perfect. 2, it says do not reject the null hypothesis when the null hypothesis is true. And this decision would be correct. Number 3 says reject the null hypothesis when the null hypothesis is true. And this is a problem. So this decision is incorrect, and this is a type of error, and the type of error is called type 1 error. And then 4 says do not reject the null hypothesis when the alternative hypothesis is true. So if the alternative hypothesis is true, that means that our null hypothesis, or H0, is false. And since we did not reject that null hypothesis, but it's false, this is a problem also. So this decision would be incorrect, and this type of error is called a type 2 error. So we have what's called a type 1 and a type 2 error, and I have it symbolized in a table right below. And so with the decision, and then right below this, you'll notice that this sounds very similar to things that we've heard. We've heard about false negatives, false positives in different testing, especially right now with COVID-19. But we also hear about this in court cases. And so there's an analogy right below this. This is the process of testing hypotheses can be compared to court trials. A person comes into a court charged with a crime, and a jury must decide whether the person is innocent, which is our null hypothesis, or guilty, which is our alternative hypothesis. Even though the person is charged with a crime at the beginning of the trial, and until the jury declares otherwise, the accused is assumed to be innocent. Only if overwhelming evidence of the person's guilt can be shown is the jury expected to declare the person guilty. Otherwise, the person is considered innocent. So you come in and you are innocent until proven guilty. And so it's like our null is what we have, what we're going with, and then our alternative is what we're trying to test. We're trying to show that someone committed a crime or maybe didn't commit the crime. So the next part says in the jury trial, there are 2 types of errors. One is the person is innocent, but the jury finds the person guilty. And this is our type 1 error, as stated up above. And 2, the person is guilty, but the jury declares the person to be innocent. And this is called a type 2 error. These 2 errors, along with the correct decisions, are shown in the table below, where the jury's decision is shown in bold on the left margin, and the true state of affairs is shown in bold along the top margin of the table. So it looks very similar to the table that we had right above. And then it says probability of making a type 1 or type 2 error. So our probability of a type 1 error is called alpha. And this is the probability of rejecting H0 when H0 is true. And then we also have beta. And beta is the probability of type 2 error. This is the probability of not rejecting H0 when H1 is true. Another way to think of H1 being true would be that H0 is false. So on the next page, we have another example. that should look familiar. This one says, according to the National Association of Home Builders, the mean price of an existing single-family home in 2009 was $218,600. A real estate broker believes that because of the recent credit crunch, the mean price has decreased since then. From the previous example, we determine what the null and alternative hypotheses are. Part A says to explain what it means to make a type 1 error, and then part B says explain what it means to make a type 2 error. So we've seen this problem already. I'm going to go ahead and zoom in a little bit so my writing's a little bit nicer, but we have H naught and we have H1. So we know that H naught's going to be mu is equal to $218,600. And then our alternative, we had mu was less than because I thought that it would decrease. So that's our null and alternative hypotheses from a previous problem. And I need this in order to discuss what a type 1 error is for this problem. So a type 1 error, and it's stated at the bottom of the previous page. So type 1 error is when we reject H naught when H naught is true. So for this problem, this would be reject H naught, and H naught's going to be that the mean home price value is $218,600 when in fact H naught is true. So when H equals 218,600 is true. So if we reject H naught, since there's only two things we have here, we have H naught and H1. So if we reject H naught, that means that we are going with our alternative. And so that would mean that we found enough evidence to conclude that the price of houses has decreased. So we need to write this in words. Zoom back out again. And so we would say the sample evidence led the real estate agent say broker to conclude that the mean price of an existing single-family home has decreased. So he rejected H naught, and so that means that since he rejected this, he is going with H1. So he had enough evidence to show that the mean price has decreased. So to conclude that the mean price of an existing single-family home has decreased. Say when, in fact. So down here says we rejected our null when the null is true. So when in fact it has not decreased. So when we talk about this type 1 error, again, we're looking at what happened and he rejected our null. And since we rejected the null, that means we're going with our alternative hypothesis, or H1. So part B says explain what it means to make a type 2 error. And I already have my null and alternative written up above, but a type 2 error is we do not reject H naught when H naught is false. So for this problem, this means we do not reject H naught, and H naught is going to be that the mean is equal to 218,600 when H naught is false. So when mu equals 218,600 is false. Well, since that is not true, that means that we go with our alternative again, because we only have those two things to select between. And if we're not going with H naught, that means that our mean has decreased. And that is true. So now writing this down with words, explaining it, this would say that the sample evidence, so the sample evidence this time did not lead the real estate broker So the sample evidence did not lead the real estate broker to conclude that the mean price of an existing single-family home So this time we did not have the sample evidence did not lead that real estate broker to conclude that the mean price of an existing single-family home has decreased when in fact the mean price did decrease. So now looking back at type 1 and type 2 errors, remember that H naught is what we're assuming is true. And this real estate broker came in thinking that the mean price has decreased. And so for type 1 error, we rejected our null. So he had enough evidence to conclude that yes, it did decrease, but it didn't. And then type 2 error, because with type 2 error, we do not reject our null, meaning that we reject H1. And that's since that's what he was testing, we don't have enough evidence to conclude what he's testing is true. So he did not reject our null, meaning that we rejected what his thoughts were, which was that it decreased. Right below this, it says level of significance. This is a fixed probability of wrongly rejecting the null hypothesis H naught if in fact it's true. This is a probability of making a type 1 error. So we can also say level of significance. It is the probability of a type 1 error and is set by the investigator in relation to the consequences of such an error. That is, we want to make the significance level as small as possible in order to protect the null hypothesis and to prevent, as far as possible, the investigator from inadvertently making false claims. So the significance level is usually denoted by an alpha, and the significance level is equal to the probability of a type 1 error, or alpha. And so usually the significance level is chosen to be a decimal, such as 0.05 or equivalently 5%. And again, usually alpha is a small value. It says an inverse relationship exists between alpha and beta, meaning that the probability of type 1 error increases, the probability of type 2 error will increase or decrease vice versa from what type 1 error is doing. So stating conclusions for hypothesis test. So we always write about, so we're going to always write about each one. And the reason why is because that's what we are testing. So once the decision whether or not to reject the null hypothesis is made, the researcher must state his or her conclusion. Sample evidence can never prove the null hypothesis to be true. By not rejecting the null hypothesis, we are saying that the evidence indicates that the null hypothesis could be true. Remember, there are errors in things, and so we're never going to be 100% confident, 100% for sure of any decision, but we'll be pretty close. And so with that said, we don't use the word accept. So we're going to use either reject or do not reject or fail to reject. We are not going to use that word accepting because, again, there could be an error involved. So on the next page, it says, according to the National Association of Home Builders, the mean price of an existing single-family home in 2009 was $218,600. A real estate broker believes that because of the recent credit crunch, the mean price has decreased since then. So the null hypothesis for this problem is not rejected. We're going to state the conclusion based upon the results of the test. I'm going to go ahead and write down our null and our alternative. And so again, we are dealing with the mean. We did this previous, and our null is going to be equal to 218,600. And then again, he thought that it decreased, so less than 218,600. And so remember, he is testing H1. That's what he thought would have happened, that the price would have decreased. And so we know that the null hypothesis for the problem was not rejected. Well, since that means that this was not rejected, that means that we were going with that. And that means that we would have to reject our H1. And so he does not have enough evidence at this point to conclude that his findings were accurate, or that we can say that the pricing of the houses has decreased. And so we'll say, and there's a basic way for writing these. So for our conclusion, we would say there is not sufficient evidence, since we did not have enough evidence to conclude that his findings that the housing prices have decreased. So there's not sufficient evidence to conclude that the mean price of an existing single-family home has decreased from the 2009 amount of $218,600. And so a couple things to note. One is that there is not sufficient evidence, and that's because it was not rejected. The null was not rejected. And the other thing is that whenever we write our conclusions, we always discuss H1, which is what we are trying to test. And so that was that an existing single-family home has decreased from the 2009 amount of $218,600. So right below this, we have another example, which is the one that we've been seeing all throughout the notes. And so this one says that in 2010, the standard deviation SAT score for the critical reading test for all students taking the exam was 112. A teacher believes that due to changes in high school curricula, the standard deviation of SAT critical reading scores are different than they were in 2010. And then it says the null hypothesis for this problem was not rejected, and then to state our conclusion. So again, rewriting our H0 and H1 values for our null and alternative hypotheses, we have that our standard deviation was equal for our null and different for our alternative. So stating our conclusion, again, since the null hypothesis for this was not rejected, that means that we were rejecting our findings. And so there is not sufficient evidence. So to conclude, we would say that there is not sufficient evidence to conclude that the standard deviation of SAT critical reading score test scores is different from the 2010 value of 112. And so again, not sufficient is because we did not reject our null. And then again, you always discuss your H1, which is what we have underlined over here, when you are writing your conclusions. So we have one more to look at. And the next one says, according to the mean monthly cell phone bill, it was $47.47 in 2010. A researcher suspects that the mean monthly cell phone bill is more expensive today. So this is a new problem that we have, and so we need to first write out our null and our alternative hypotheses. So the first question is, what is the parameter? And it does say mean monthly cell phone bill, so I'm going to go ahead and put mu for both of these. H naught does get an equal sign. And it does say more expensive today, so meaning more expensive, my alternative is going to be greater than. And then that amount that we are going to have is that $47.47. And so for this problem, it says the null hypothesis for this problem is rejected. So that means that we are rejecting H naught. And our findings, we're actually going to be going with and saying that we don't reject those. And so we have to state the conclusion based upon the results of the test. So in conclusion, there is sufficient evidence. And so we have enough evidence this time because we rejected our null hypothesis, and our test that we were testing, our hypothesis H1 is that the mean monthly cell phone bill has increased, it's more expensive today, and we have enough evidence to conclude that. So we have sufficient evidence to conclude that the mean monthly cell phone bill is more than it was in 2010, that $47.47. And so again, you always discuss H1. And then also, there is sufficient evidence since we rejected our null hypothesis. So right below this, we have what is called a test statistic. And a test statistic is a value in making a decision about the null hypothesis. It is found by converting the sample statistic, such as p hat, x bar, or s, to a score such as z, t, or chi-squared, which we have not yet talked about. But we have looked at z and t distributions with the assumption that the null hypothesis is true. And so down below we have a table with our parameter, the sampling distribution that we'll look at, requirements that need to be met, and then the test statistic that we have. Below that we have a critical region or a rejection region. And this is the area corresponding to the values of the test statistic that cause us to reject the null hypothesis. So on the next page, we have where it discusses there's 3 different methods to actually conduct a hypothesis test. And we'll talk about all 3 of them briefly, and then talk about the one that we will mostly be focusing on at this point. And the first one that we have is a traditional method. And the traditional method says you're going to find your critical value that corresponds to the significance level. And again, your significance level is your alpha. And alpha is usually going to be a value such as 0.01, 0.05, and 0.1. However, it could be something different, but these are the most 3 common ones that we have. And second thing says, if the test statistic is in the critical or rejection region, then we're going to reject the null hypothesis. Otherwise, we do not reject the null hypothesis. And so there's 3 pictures there. We have a 2-tailed, left-tailed, and right-tailed setup. And you'll notice that these 2 tails over here, the shaded area for our first image, these are going to be our rejection region. And since this is a 2-tailed test and our significance level would be alpha, that alpha gets split up into 2 parts. So this is going to be alpha over 2 for each of these. And so this is going to be our rejection region. And if the test statistic is in these regions, then we reject our null hypothesis. Otherwise, we do not reject our null hypothesis. This is the same for a left-tailed. However, your rejection region is only going to be on that left tail. And same with the right-tailed. So again, this is your rejection region or your critical region. We also have a p-value method, and before we get into that, let's discuss what a p-value even is. So a p-value is a probability of getting a value of a test statistic that is at least as extreme as the test statistic obtained from this sample data, assuming that the null hypothesis is true. So that's by definition. In a little bit simpler terms, it's the probability of what you observe occurring randomly if the null is true. And so the next method that we have is our p-value method, which is actually going to be our mostly used method for this class. So we have a couple steps here, and the first thing that we're going to do is we are going to find our p-value, and this is going to be done on the calculator. And remember, the p-value is the probability of what you observed occurring randomly if the null is true. And once you have your p-value, you're going to check to see if that p-value is less than or equal to alpha, or your significance level. And this means that it's going to be in the rejection region or that critical region. And then that means that we are going to reject our null hypothesis, or H naught. And so again, two-tailed, left-tailed, right-tailed, the same thing. These are still your rejection regions, those shaded areas that we have, which is where you would reject your null hypothesis. Then we have a third method down here, which is our confidence interval method. And this says if the confidence interval contains the population parameter. So if it contains the population parameter, then we do not reject the null hypothesis. But if our confidence interval does not contain the population parameter, then we're going to reject our null hypothesis. And confidence intervals always need to be set up as a two-tailed test. So for us, again, that main method that we're going to be using will be the p-value method that we have. And so to use the p-value method, a conclusion in the hypothesis test, compare the p-value with alpha. And so we have two different things that can happen here. If the p-value is less than or equal to alpha, then we reject H naught. And if the p-value is greater than alpha, then we do not reject H naught. And so a little saying is, if the p-value is low, you let the null go. So that chance of it happening is low. And so if it's less than or equal to that alpha, that significance level, then we're going to reject that H naught. So if the p-value is low, you let the null go. So again, the p-value is the probability of getting a test statistic equal to or more extreme than your sample result. If the p-value is greater than the level of confidence, then we can say that the probability of a more extreme test statistic is larger than the level of significance, and thus we do not reject H naught. If, on the other hand, the p-value is less than the level of confidence, we conclude that the probability of a more extreme test statistic is smaller than the level of confidence, and thus we're going to reject our null H naught. So on the next page we have some examples. The first one says, suppose we are testing the hypothesis H naught, which is going to be p equals 0.3 versus H1, which is going to be p is greater than 0.3, and we find that the p-value is going to be 0.23. Let alpha equals 0.10 and explain what this means, and would you reject the null hypothesis and why? So a couple things, there's a couple questions here. First one, what does it mean? So this says, if the p-value is equal to 0.23, we would expect results at least as extreme as the test statistic in about 23% of the samples. But again, this is assuming that the null is true. So if the null, which in this case our null is p equals 0.3, is true, and so it says, would you reject the null hypothesis and why? So in order to determine this, we have to compare our p-value, which is 0.23, to our significance level, or alpha, which is 0.10. So since our p-value is equal to 0.23, this is going to be greater than our alpha, which is 0.10, which again, both of these were given to us. Our p-value is 0.23 and alpha is 0.10. So since our p-value is greater than alpha, this means that we do not reject H naught. Another way to say this would be fail to reject H naught. The next example says the test statistic of z equals 1 is obtained when testing the claim that p is greater than 0.3. Part A says identify the hypothesis test as being two-tailed, left-tailed, or right-tailed. And since we know that our null would always have an equal sign, this right here is going to be what we're testing, and that's our alternative hypothesis, which means that this is going to be a right-tailed test. Part B says to state your null and alternative. So our alternative is going to be that p is greater than 0.3, and then our null would be p is equal to 0.3. To find our p-value, we need to do a little calculations here. So again, the p-value is a probability. I'm going to go ahead and sketch my normal curve so we have a visual representation of this. Since it is talking about z, I know that I'm dealing with a standard normal distribution. And with a standard normal distribution, our mean was equal to 0 and our standard deviation is equal to 1. So I'm going to go ahead and put 0 on here. Since z is equal to 1, I'll put that value on. And so this would be z is equal to 1. Since we're dealing with a right-tailed test, I know that I will be shading that area to the right of z equals 1. And this area here would be our p-value. So our test statistic is z equals 1, and anything more extreme than that would be that p-value. And so to calculate this, we're going to use normal CDF, since this is a normal distribution. And our starting value is going to be 1. That's where our shading starts. Shading goes on forever. Remember, we use 1E99. Our mean and our standard deviation, so 0 and 1. Close your parentheses, and rounding 4 decimal places, we get 0.1587. Part D says using the significance level of alpha equals 0.05, should we reject H naught or fail to reject H naught? And it tells us for this problem to use the p-value approach. So since we know our p-value is equal to 0.1587, we can compare this to alpha, and alpha is equal to 0.05. And so we can see that the p-value is definitely greater than alpha. And since our p-value is greater than alpha, this means that we are going to fail to reject H naught. Or again, another way to say that is do not reject H naught. So the next one that we have is to find the critical value. And this corresponds to our significance level, which is alpha equals 0.05. So I'm going to go ahead and draw a normal curve so we can look at this. And again, we're dealing with a standard normal, so I will put z in there. We're dealing with a right-tailed test. So I'll put a z value over here. and I'll call it Z sub C. So I'll put CV for critical value. And this area to the right is equal to alpha. And so to find Z sub CV for critical value, we need to use inverse norm. And our area to the left, since the area on the right was 0.05, that means that this unshaded area is going to be 1 minus 0.05, which equals 0.95, comma the mean, which is 0, and the standard deviation, which is 1. Working this out, and I'm going to go at around 3 decimal places, I get 1.645. And so the next thing that we have says to use the significance level of alpha equals 0.05, should we reject the null or fail to reject the null? And this time it wants us to use that traditional method. So again, we already know that we are going to not reject H naught or fail to reject H naught, but we use the p-value approach up above in part D. And so now we're going to be using our traditional method, which we don't see quite so often. And so again, with the traditional method, we need the critical value and the test statistic. So we need our critical value and test statistic. So I'm going to go ahead and draw a bell-shaped curve. And again, we're dealing with that standard normal, so I'll put 0 in the middle. And we know that that critical value Z that we found was 1.645. So I'm going to put that on here. This is 1.645. And from that critical value that we have, and I'll put down critical value. And so that area from the critical value, since it is a right tail test to the right, is going to represent our rejection region or our critical region. So this part right here is our rejection region or critical region. And so since our test statistic was given to us, we know that the test statistic is just going to be Z is equal to 1. I'm going to go ahead and put that on my graph. So here is Z is equal to 1, and this is our test statistic. And for this problem, it was given to us. A lot of times you have to calculate it on your own by a z-score. And since our test statistic is not in that rejection region, so since test statistic is not in the rejection region, we can say that we are going to fail to reject or do not reject H naught. And again, you could still say fail to reject.